started recording. Okay. Good evening, everyone. I'm Gangadhar Venkatramana. Today, we are here to another session of fundamentals of theoretical and experimental aerodynamics, the problem-solving session. And the course instructor is Professor Arnav Roy. And we are going to see the recap of last week content, and unsolved problems in the last week, and the content regarding the week 4 and week 5, and that we had that already covered in this NPTEL course. So it's a kind of brief review and some problem solving sessions. So let's start our session without any delay. Before starting the session, I just want to know if there are any queries up to the last week's session, or you would like to ask before the starting the session related to the course content or anything that you want to ask.
Yes, sir.
Yes, sir.
Sir, I want to ask you that that quasi one-dimensional flow in a convergent divergent nozzle, that concept
Okay.
I cannot understand. Means I have watched those recorded videos of Professor, but
so you are not able to understand what is that quasi one-dimensional flow in convergent divergent nozzle.
Yes, sir. Sir, actually, in that videos, Professor told that in this type of flows, means when a flow is subsonic and it at the convergent part, it comes to the sonic regime, and after that it will accelerate to supersonic. But if the flow is supersonic, it will come to the convergent part sonic and it will become subsonic. So sir, means I can't understand this concept, why it is happening, means why it is completely reverse. Because with the continuity equation, if we apply, then we know that if area decreases and velocity will increase. Therefore, we can say that Mach number will increase or anything like that, sir. We can, if we want to relate. But sir, in this case, the completely opposite thing is happening. What is the main reason behind it, sir?
So he did not explain the reason, or he just give you the overview.
Sir, if you can elaborate it. Actually, he said, sir, but not.
You're not clear.
Yes, sir. I was not clear about it.
Okay, I will try to explain that today, maybe at the end of the session. Is that okay for you?
Yes, sir.
Because it needs some time. I will take some time at the end of the session, maybe 15 minutes at the end of the session. Then we can clearly elaborate it.
Okay, sir. And another doubt I have, sir, that I posted in that questionnaire session also. Means below the video there is a tab. In that I have posted that in characteristic flows, means that in case of expansion fan and compression corner, when it is forming, sir, in case of expansion fan, if we means draw the characteristic line backwards, then it will start from a point. So is it possible that,
can you repeat again? In the expansion fan,
in an expansion fan, if we look at the characteristic lines, means, we can say that if we take an example of compression corner, for example, that in case of compression corner, the characteristic lines will converge and it will form a normal shock.
Yes.
But in case of expansion fan, the lines are diverging. So I am just telling that, sir, if we imagine, means it is completely hypothetical, that if we are taking this divergence characteristic line, then it will start from a point. And if it starts from a point, then if we draw it more backward, then is it possible that from a normal shock, is it possible that expansion fan occurs?
from a normal shock, expansion fan occurs. You want to draw expansion, the characteristic lines backward in, like
Yes, sir.
according to your question, I read your question. Like you want to
Yes, sir.
draw characteristic lines of the expansion fan instead of forward, you want to draw in the backward direction there.
No, if we just conceptualize the visualize the thing, if we draw the characteristic line, because in case of compression corner, we can see that the lines are converging and it is meeting at a point and forming a normal shock.
Okay.
So, sir, just means reversing the whole case in case of expansion fan. Is it possible or?
Okay. Let me draw your. Let I will just try to draw your question. Let me know whether it is the same thing or not. So you have a. Let's take another point. You have a compression corner. You are getting a oblique shock wave, right?
No, sir. If we consider normal shock only,
If you are considering normal shock in what? Normal shock in a piston flow
so
through a pipe
actually
with a piston.
yes, sir. Actually, means professor has drawn that characteristic line graph he has shown, and in
Okay.
that graph he has just means the in the preliminary discussion of this expansion fan and compression corner means formation of normal shock. In that graph,
Okay.
he has just shown the characteristic lines, and after that, he has gone in depth in compression corner and expansion fan. So in that preliminary discussion, I just asked means that question in that video. Yes, sir, like this only.
So if your waves are like this, these are all compressing. It may form a normal shock or a oblique shock, right?
Yes, sir. In this case, it will form a normal shock. It meets at a point and it will form a normal shock. I think so.
Okay.
Yes.
Hmm.
And in case of expansion fan, if we draw the graph,
I draw the graph in case of expansion waves.
so if we now just
Hmm.
draw these lines backward and try to imagine it from a point, then is
Okay.
it possible that means I am just reversing the whole case basically?
So I will just, you are saying that whatever the lines that are going this direction, okay, I got it, you clarity. Like these lines, while you are drawing also, those should be physically exist.
Yes, sir.
Let me tell you what is the thing is, you cannot directly draw some lines with like in the xt plane. If it is this is xt plane,
Yes, sir.
it is not physically possible to draw some lines randomly in the xt plane. These lines should follow the characteristics of the physics undergoing either in the piston flow through a piston pipe or flow in any kind of flow that should be physically exist. Then only you can draw by tracing that particle along the x direction and its time, right?
Yes, sir.
So to more clear understanding of yours, suppose I consider this is as my x and this is my t, okay?
Yes,
And
sir.
at this point, my expansion waves are forming. Expansion waves alone cannot exist. Your doubt is correct. But when the flow is already exists as a flow over this kind of corner, if you are diverging like this, here expansion waves exist like this.
Yes, sir.
And these waves will reflect back into the flow domain like this. This
Okay.
wave here is this I drawn. you should be clear like which physics it is going to show you. These are expansion waves, and those are
Yes, sir.
traveling in the flow field with respect to time. Okay, and then
Okay, sir.
here it is a wall, that is some wall you have at x equals to 0. Suppose you have some wall here, and after touching this wall these waves reflect back.
Okay,
This
sir.
is corresponding to flow because of blast of a aluminum foil or blast in a pipe. This is a high pressure P naught, and this is a low pressure P. If this is a very high pressure, assume this is around 200 times than this right side pressure. So if you suddenly blast this wall, whatever the wall you are seeing, if you suddenly blast this wall, you can see a normal shock wave traveling here and expansion waves traveling this side. Whatever you are saying, like if I draw lines backward characteristics, that kind of phenomena exists here.
Okay, so in
Expansion
case of
waves, yeah.
shock tubes.
In case of shock tubes, yes, this is what we call the shock
Okay.
tubes. So in the shock tubes, your normal shock and expansion waves both exist together. They cannot exist individually because it starts from the
Okay.
zero relative velocity, right?
Yes,
So
sir.
both your normal shock exist and your expansion waves exist, and whatever the concept you are trying to visualize, you can understand from this shock tube and the backward running characteristics or rightward running characteristics. If you draw those two, you can see. But expansion waves, leftward running and rightward running, those different for expansion waves because these are um like I can say for the shock wave, those are both are the finite kind of waves, but you can write you can draw the characteristics. I don't know whether this is clear for you or not. These kind of characteristics were explained for you in the class. I did not go through the entire
Yes.
material. These kind of
Yes, sir.
characteristics. So in the expansion fan itself you can draw these kind of waves, but this is nothing but like looking like a drawing in a backward sense. As this is going in the leftward, you are drawing in the rightward, but these acts as a, they don't act as, I mean, another kind of family, but it creates no difference in the flow field. Like
Okay, sir.
characteristic waves are there, those acts as a waves, but physically whether it is present or not, that you mathematically can represent, but this does not create any influence on the flow field. In case of expansion waves, even here in the compressor corner, you can draw some lines that are like this. This is the expansion fan. The characteristic lines you can draw like this is it will create a nonlinear family of curve. A very curvature kind of things will happen here. These characteristic lines or like not straight line. If these characteristic lines, if you try to draw in this expansion fan, this is one characteristic line. And if you are drawing at this point, this is right running or this is left running, these characteristic lines also present, but does not represent the oblique shock wave. You're getting? You
Yes,
try
sir.
to draw the things in the flow phenomena, then you will get a clear understanding. Here,
Okay, sir.
though you were leftward running, backward running of the expansion wave, those are expansion wave that does not form a oblique shock. But you should be clear, right? When it is a shock tube, the rightward running creates a normal shock and leftward running creates a expansion wave. But in the expansion wave, again, if you draw the characteristic lines clearly, there will be another family of curves that does not influence anything in the flow field. But you can draw, and it will be helpful while solving for the properties of the flow field in that point. You can get much more clarity of these kind of waves by studying in detail of this shock tube. You can find in Anderson books, John D. Anderson.
Yes, sir.
So how you can draw this? Because I can say that professor gave you overall view of how these expansion waves work, how these oblique waves work, but not in detail or in detail mathematics of it, right?
Yes. Yes, sir.
Don't get confused with backward direction. If you write, even though if you are converging at this point, if you draw in the backward, it won't create any oblique shock wave in the flow field because flow is already anyway. You always need to see only one thing, which direction your flow is moving. Your flow is moving in this direction, right?
Yes, sir.
If flow is moving in this direction and sound is also traveling in forward direction, any wave is there, and if your flow is supersonic, disturbances cannot propagate in the disturbances cannot propagate to the backward direction. So it cannot sense something what is happening, whatever the flow is coming here, if it is greater than Mach number one, whatever the happening here, this flow is, I mean, the backside flow cannot experience that. Backward flow means, I mean, the, sorry, this is the downstream. Yeah, downstream flow. Sorry, let me clear. Sorry, this is upstream flow. So whatever the flow present here, I just confusing with the upstream and downstream. Whatever the flow present here, it cannot experience that. So it is like you can understand from here itself. So it cannot form any kind of oblique shock in the backside direction, right? Flow. Your flow is
Yes,
all
sir.
supersonic
Got it.
here. Got it?
Yes.
Okay.
Yes, sir.
Okay. Any other questions?
Sir, the last assignment question, it was written that bound
Bound
vortex only.
vertex. Yes.
Yes, sir.
I clarified that question that I forgot to mention you. That question actually asking us why the bound vertex concept or the Brandel layer, Brandel, what he's trying to do in that finite wind theory. He is trying to do, suppose if it is your finite wind, even if your infinite wing airfoil, what is the primary thing that we need to model around the wing? The
Sorry, sir.
primary thing that we need to model mathematically.
Bound vortex only. Then
Bound vertex is the one from after the yes.
after
After
that,
that,
the trailing vortexes. Trailing
trailing
vortices
vertices.
means
So from there, question starts like, what is the Brandel? What is the complete question of it? Brandel approximation, like what he is trying to approximate there with that
yes, sir.
for a finite wing. He started hint also given that you already mentioned, but I did not see it clearly. I was
Yes, sir.
reading only the question. So, and I later on realized that they're asking only for the wing, not in the they don't want to model the trailing edge vertices or the velocity in the wave.
Yes,
So
sir.
the good approximation, how you can approximate uh, this lifting line for a finite wing is to first model the bound vertex. Right? For modeling the bound vertex, they
Yes, sir.
started using this vertex filament. Right?
Yes, sir. That these two trailing vortices.
Yes. And then they tried, because it cannot end in the free stream. Like if the vertex filament is there, you cannot stop the vertex filament in the flow.
Yes, sir.
It always continues.
No, sir.
So yeah. It,
Yes, sir. It is finite basically.
no. This what I mean vertex filament I'm telling. Saying about the vertex filament. Don't confuse. If you have a vertex filament, there is any verticity or vertex with the strength gamma, it cannot end at any point. It should continuously move from, I mean, infinite to infinite. Like in
Okay,
physics,
sir.
if you see, you don't get confused. In physics, if you see, if you are having a uh, domain and there is a presence of vertex here, its strength exists everywhere in the flow field. You cannot say its strength does not exist somewhere in the flow field. That means it cannot end anywhere in the flow field. In the same way, if you have a vertex filament, it vertex filament cannot be end in the free stream. And these are all combinations of vertex placed along the filament. So it cannot end in the free stream. So we model that by making it as a trailing edge vertices in the form of horseshoe vertex. So this is the horseshoe vertex as a secondary modeling. The primary idea is to model the bound vertex only. And this represents your trailing edge vertices. You are still not here.
Yes, sir. Got it.
Okay. If it is not clear for you, let me know. I will try to help you.
Clear, sir.
Okay. And any other question? Any other person here? or if you have any other queries. Okay, if no queries, I will proceed with the today's class. Uh, Let me give you a brief overview what we discussed in the last class. In the last class, we seen the substantial derivative. It's a review kind of thing, but I'm just showing the things what we discussed long class. So it will help you for later on for writing your exam and for future concepts also. So substantial derivative, to calculate the substantial derivative of any parameter, and then uh, like I think it is already recap, so I don't want to recap these kind of concepts again. Let's directly go to the problem solving. But the key important parameters are there. You can just look over the slides what we discussed from the last session, so that we can complete two more problems that we left in the last session. Okay. This question we complete. These all questions we completed in the last class. Yeah, we left here. So we are at question number 8. In this, the question saying a light plane flies at 160 km per hour in standard A at an altitude of 1000 meter. And what will be the stagnation pressure at the leading edge of the wing? It's a wing, but we are not considering it's a trailing edge vortices or anything. We are considering it as an airfoil. So the question is, stagnation pressure, we need to calculate. Stagnation pressure occurs at the leading edge of the airfoil, that is at a point A. And another information what we have, at a certain point close to the wing, the airspeed related to the wing is 55 meters per second. That means at a certain point means at the point B, we have velocity is 55 meters per second. Also determine the pressure coefficient at this point at an altitude of 1000 meters. It is given that altitude the respect to free stream pressure and free stream density. Assume the flow to be incompressible, inviscid, and irrotational. So these are the primary assumptions that we need if we want to apply the Bernoulli equation. So let's start the question. It is direct application of your Bernoulli equation. How you can approach is you have that v free stream velocity 160 kilometers per hour. That is 160 kilometers per hour. If you convert that to the meters per second, you will get 44.44 meters per second, because we want to use the same metrics, same system of units. So then how you can calculate the stagnation pressure? Stagnation pressure at point A can be P naught at A, that is corresponding to the stagnation pressure at point A, that is equals to static pressure in the free stream plus half rho free stream velocity square. What is your free stream static pressure? It is 8.96 times 10 to the power 4. We just substitute that 8.96 times 10 to the power 4 plus half. You have density of free stream density is 1.12 kg per meter square, sorry, kg per meter cube. And the corresponding velocity we just calculated as 44.44 meters per second, that is square. And after substituting, we will get stagnation pressure at the leading edge equals to 90705.9 Newton per meter square. So first thing we did, the stagnation pressure is done. And the second thing we also need to do is determine the pressure at this point. That what is the another point? That is the point B. We need to measure the static pressure at this point. We have the information of velocity. Again, we need to apply the same thing. We can apply either by using the static pressure with respect to the free stream or the stagnation pressure. I will just take the stagnation pressure 90705.9 is Newton per meter square is your stagnation pressure at point A. And then I will say PB as my static pressure at that point B. plus half rho. We have velocity at B is 55 meters per second, but according to Bernoulli, it is 55 square. We should half rho V square. Please note that here it is a velocity of 44.44 meters per second, and velocity at B is 55 meters per second, right? So, uh, what is the important thing that we need to understand is the velocity of your free stream is always less than the velocity, like some point on the airfoil always reach a maximum velocity which is always greater than that your free stream velocity. That's why your Bernoulli equation is also, if the velocity is less, what will show your Bernoulli equation should also show a less static pressure, that is, that should be less than the free stream static pressure. Though we are calculating with respect to the stagnation pressure at point A, everything is interrelated. Everything governs by the Bernoulli equation. So what we should get PB should be less than P infinity of the PA. So if you calculate for the PP, because that is the only unknown, you have density also 1.12 kg per meter cube. So just substitute that, you will get PB equals to 90, sorry, 8 89011.95, which is less than our free stream static pressure. This decrease in the static pressure, like it not only decrease at this point, every point, if you can calculate like this, each and every point discrete data or a continuous data, you will get the overall pressure distribution. From that, you can also calculate the overall lift distribution or the net lift force on this airfoil. So that is the solution of this problem. We can move to the next question. This is a simple Bernoulli application. Now, next problem, we have, we need to find out, uh, consider the flow field given by V bar equals to minus 2a by I cap, some velocity vector, where a is a constant. Okay. For the given flow field, dash and velocity potential. So two things we need to calculate here, like whether the flow field, according to the options they are saying, is whether the, find first whether the flow is rotational or irrotational. If flow is rotational or irrotational, like instead of checking it, I can say the flow is rotational, because you have four options here, and in these four options, you all have, I mean, we have the pi given readily, like that is the velocity potential. But from our understanding, we know that the potential function pi only exists if del cross V bar equals to 0. That is, if the flow is irrotational. So, if the flow is irrotational, then only your pi exists, but you have pi option for all the options. So, definitely this should be either irrotational of A and B, option A or option D. So, now, anyway, it is our, for your understanding how to calculate that del cross V. Again, we will just have a look, because it is just a two-dimensional flow. We can just re-verify whether it is irrotational or not. For your irrotationality condition, we need to satisfy the del cross V bar equals to 0. For a two-dimensional case, it will come as half dou V by dou X minus dou U by dou Y. It is the angular velocity we are calculating, that nothing but the same as your irrotationality condition. So if you substitute your V component, that is minus 2AX, okay, and you have minus here, dou by of U component minus 2AY, you will get 0. K cap, this is K cap. Don't forget the vectors that we are mentioning. So it will give you understanding of what is the different vector calculus operations that we are following. If it is you are doing IJ as participating in this curl, so we will get vector, unit vector in the K direction. So now we verified that flow is irrotational, and the second task is what is the velocity potential function. Since your del cross V bar equals to 0, I can write this del cross del pi equals to 0. That's how we get a potential function pi or velocity potential. Velocity potential. How you can find out this velocity potential? By expanding this, you will get dou phi over dou x equals to u and dou phi over dou y equals to v. So just write that dou phi over dou x equals to u component is 2ay and dou phi over dou y equals to v component is minus 2ax. So these are your two components of x and y. Let me try to solve for the x component. If your dou pi equals to minus 2ay, dou x is substituted u component yes. And if you integrate it, you will get pi equals to minus 2ayx. This is minus 2ayx plus, since we are integrating with respect to partial differentiation of x, you should get some function of y, right? Minus 2ayx. This is the first one. That means first equation of the pi. If I do this by dou pi over dou y for the applying for the equation one, this is my pi equation that I got. So if I try to apply dou phi over dou y, it should be equals to my v vector. What is my v vector? Minus 2ax. But it will come as, like if you do dou phi over dou y for equation 1, it will gives you as minus 2ax plus f dash of y. Just compare this one and this one. Since your f dash of y is not present here, that should be equals to, if you just match the equation, that should be equals to 0. That means if you convert it back, if you convert this f dash of y equals to 0, then you integrate it, then your f of y should be a constant from this. If your f dash of y equals to 0, f dash of y means dou f by dou y, that is equals to 0, then if you integrate back, then that f of y should be equals to constant. Then now we get the f of y. Substitute back, that is a constant c, back to the equation. Then pi equals to minus 2ayx plus c. That is our solution, right? So irrotational and pi equals to minus 2ayx plus c. Okay, this is these are the all questions. Let me see whether we finish the remaining questions or also not in this. Yes, this one we discussed last time. And this one also discussed. Okay. So all the questions in this we discussed, but last time I noted few questions. That is question number 9 from assignment 5. Arhit asked last time like regarding the doubt, and I just explained that like what happening in that question at the beginning of lecture. And one more thing he asked is what is Konda effect. So for your better view,
Yes,
would you like to see what is the Konda effect? Like have you googled it? Like how what
yes,
is
sir. I
Konda?
have Googled it. Means in Google, I have not searched deep into it. I have just searched what is Fonda effect, and it shows the phenomena to attach with of the means the attachment of the flow with the body. Means
Okay, you get it.
it
Like
is
you are not able to
yes, sir.
understand that.
I got it, but why this phenomena is happening? I just want to know that. Yes.
Okay, this science is also there. They described in Wikipedia. Actually, what I remember from the last time, I told you that it is more or less same as Magnus effect. If you see the Magnus effect, also if you compare it, you know the Magnus effect first of all.
Yes, sir. Yes, sir.
Yeah, it
Yes.
will more or less depicts the same kind of scenario, but Magnus effect needs this one what we say a rotating kind of fluid body, a rotating kind of body. So here
Yes, sir.
also we need, I will show you that in Wikipedia
Sir,
they, yes.
basically, sir, we can we can say that in case of Magnus effect, the best example we can give is the spinning of a ball. In
Yes, spinning of the ball. But there also it is have a thing. Like
uh,
you can find the similarities between both. Magnus
yes,
effect
sir.
in the
But
spinning of
in
the ball.
yes, sir.
Yes.
And in case of quanta effect, the it is just showing that the phenomena, the means condition to attach with the flow with the body, means the
Yes,
phenomena
but
due to which it attaches.
yes. Let me try to clear you that. So this is the figure that is illustrating your Conda effect. Can I take a pen here? I don't know. Never tried. Can we take a pen on the edge? Okay, no worries. I will try to
No,
explain
sir.
with pen. Okay, I will try to explain with my cursor. So I think you can see my cursor. Suppose you have a jet that
Yes, sir.
is emerging from a orifice, this kind of orifice or a pipe. What is if the high speed flow? Do you know that with whenever like any kind of jet that is emerging from the pipe like this, it will creates a low pressure region on bottom of it because of this high velocity here and a low velocity in the atmosphere. This is ambient atmosphere that is low, I mean high pressure, and this is also ambient atmosphere, and you are having a velocity of high, I mean some high velocity compared to your ambient. So this velocity difference this will create a low pressure region here. So the fluid present there will try to entrain into this core jet. We call it as a core jet. Okay, because of this pressure difference. If you see like, um, have you ever encountered like flow through a nozzle or like anywhere in your best example is the releasing of jet from a pressure vessel at your cycle tank. Have you ever tried to release the a core
Ye-
jet from your?
Yes, sir.
Yeah, can you
Yes, sir.
find the difference of pressure? It will create a low temperature or low pressure at that region. Did you sense that before?
No, sir. I haven't.
The same. Yeah, you can try once if you release that air and if you try to place your finger near to that jet, you can see a low temperature also and low. You can see the difference, not pressure, but you can see the temperature difference. So the same thing because of the temperature difference. If the, how that depends on the velocity of the fluid also. If the velocity is so high, then only you can sense it. So this will create. This is the ambient pressure, and this is your also ambient pressure on both bottom and top of the surface, and this is your high velocity. Because of this high velocity, and there is also fluid forces, that intermolecular forces that exist, and that drags the velocity here in the ambient. As it moving very forward, it drags the velocity or fluid present nearby in the surroundings. That is called we call as entrainment. Okay, with this entrainment of fluid, you can see from the both on top it is happening. If you do the same thing for uh, like placing a orifice of jet close to the surface like this, now fluid can enter from the top surface like this. That is only ambient fluid that above the core jet, above this jet can enter into the fluid. But from the bottom, there is nothing to enter. But we already seen that there is a formation of low pressure, not in the jet, not inside the jet. Remember, low pressure is not forming inside the jet. If some jet is coming out of the, like, I don't want to confuse you, but one thing you should remember, if some jet, some fluid is coming out of the orifice and entering into the atmosphere, that its pressure itself will equivalent to the ambient pressure. That means the same pressure that we are feeling in the surroundings. That you should always keep in mind. But its velocity is making the differences here. Since it has a very high velocity, it is dragging the fluids surrounding by and making the creating a low pressure zones here. And this low pressure zones, because it's creating an additional velocity in the ambient fluid because of the drag, and the fluid also present in the atmosphere that is entering into this core jet. Okay, it is able to drag the fluid on the top surface, and it is creating a low pressure here, but not able to drag the fluid on into this, right? Since it is having a low pressure
Yes.
here and it is dragging the fluid from this side, and inside also it is almost it is equals to your ambient pressure, but have your it is forming a low pressure zone. What it can do, it needs to satisfy everything. That low pressure should also satisfy here, but there is no fluid. So after certain point where whenever this kinetic energy becomes sufficiently strong, I mean sufficiently less to diverge like this because of this low pressure zone, at that point it will tend or it will bend and attach to the surface. Like it should satisfy both the kinetic energy and the core jet should be less than your, like it should able to bend due to this low pressure region, whatever the low pressure region is formed due to the dragging of the fluid from the surroundings. You're able to understand now what is why it is tending
Y- Yes, sir.
to the surface. Okay.
Yes, sir, I got it.
Yeah. Now this is with respect to the static plate. If you're dealing with respect to the static plate, this is what happening. But if you are dealing with respect to a moving fluid, a spinning ball here, it is also like now you can see the Magnus effect. Why this ball is you are push your uh, I mean what we say you are ejecting some air from through this nozzle and you are making a flow, pushing this ball on at this some ball here, and whether it is spinning or not that we say secondary, but the same phenomena first will occur, like what Honda effect is there, that same will occur here. But why it is staying there at that some point with the flow of air like this? Air is not a rigid, it can easily fall, right? But we know from the Honda effect, the flow what is
Yes, sir.
happening over this ball will stay with this. At the same time, if the ball is also spinning, spinning ball and incoming flow, and the flow is also attached. What is representing? Are you able to connect with the Magnus effect?
Yes, sir.
And the spinning ball is also staying
Yes,
at
sir.
that height. That is flow over a rotating or a spinning cylinder. That is creating a lift and and a component of a lift or a resultant forces, and it is staying here, right?
Yes, sir.
It is balancing. So that's why I like connected with this Conda effect, and this makes me confused several times. Like Conda effect and Magnus effect. So any doubts on this?
Yes, sir. I have means if we want to connect this quanta effect is means we can the application we can easily see in case of airfoils. So
The application we can see in the case
hello,
of airfoil. Yes, yes, yes. Okay. Hello.
hello,
Yes, can you hear me, Arhit?
sir. Am I audible?
Yes, yes, you are audible. Hello.
Yes, sir.
Am I
Yes, sir. Sir,
audible?
actually, I am saying that.
Okay.
Yes, sir. Sir,
Okay,
actually,
okay.
I'm saying that if
Hmm.
connect this quanta effect, means we can see the application in case of airfoils.
Okay.
Sir, but in the case of stalls, the formation of wakes at the means near to the trailing edge, sir,
Hmm.
why basically those wakes form? Means due to the adverse pressure gradient forming near to the trailing edges. Means are those adverse pressure gradient more than the ambient pressure gradient that forms the wake at near the trailing edge?
No, no, no. You are confusing with the both. It is flow separation happens due to the adverse pressure gradient. That's true. But even it is like on the surface you need to see. Above the surface you have a velocity, but on the surface you don't have any kind of velocity. Let me show you. This is a flat plate. In the flat plate you don't see any adverse pressure gradient, but on the curved surface if you see, you will find at some point your velocity acts like this. Oh, sorry. So if your velocity profile is like this at some point, your flow cannot move any way because it is almost zero velocity here, as your dv by dy is equals to 0. So it can only do that is separation from this surface. So from this point, your separation occurs because it is purely due to the viscous effects. Okay.
Yes, sir, got it.
Okay. So it is not with dealing with any kind of quanta effect. It is clearly because of your viscous effect this separation is happening. So it cannot attach all the
Okay,
time.
sir.
If there is no viscous, it always attach. Okay. Any
Okay,
more
sir.
questions? I think there are two more people. Mithul and A20. There is no name for it. Yes, Mithul, do you have any questions?
No, sir.
Okay, thank you. So, if no questions, today I would like to discuss more on the reviewing of concepts. So we will see problem solving of the current session that what I'm going to do review. We will see this problem solving in the next session. So let me start another presentation. Give me a minute. Yeah. So today we will see some review of concepts on base airfoil and a finite wing. Like the theory that you had already learned during lectures, or you might have watched the lectures for your assignments or everything. I think you did everything, but uh, it's a kind of review for you so that in the next week you can solve the problems easier, or whatever the problems I'm discussing you can understand, because we all in the lectures we have already crossed many important concepts. So I will quickly review these important concepts of finite infinite wing, that is nothing but airfoil, and the finite wing concepts. So first of all, we are dealing with the airfoil geometry. In this airfoil geometry, I will first draw a symmetric airfoil. This is all you know, but maybe some conceptual of mathematics can help you for future or problem solving. And this is the cambered aerofoil. The line that joins leading edge and trailing edge, this is your leading edge, and this is your trailing edge, and this line is called the chord line. But the cambered aerofoil, this is your chord line, and this is your mean camber line. Okay, the mean camber line is the key line that generates your cambered aerofoil or asymmetry in the aerofoil. For the symmetric aerofoil, your camber line or chord line both are same, so there is no asymmetricity you see on the top or bottom surface. But in the camber line, if you have any line like this, suppose this is the camber line, you need to move the same distance as you move upward and downward from the camber line. That will generate your aerofoil from both the top and bottom surfaces. This is how you can generate your cambered aerofoil. So these are the important terminology, and thickness is also key parameter for your symmetric and asymmetric aerofoils. The thickness, maximum thickness generally locates at, it's not discussed anywhere, but you need to understand like where is the maximum thickness location. It is around 0.3 of with terms of chord, 0.3 times of chord. Your maximum thickness location is present. So then you have what is normal force. The normal force that is perpendicular to your chord line. This is your normal force. And this is your axial force A. We represent the normal force with letter N and axial force with letter A. I'm sorry for the writing, it's not so good today. And then we have, I think we discussed many queries in these concepts last time, like moment about the leading edge. Moment about the leading edge is the normal force times x Cp, where Cp is the center of pressure location, and it is clockwise or counterclockwise that we generally indicates. Like if it is a pitch of motion, then it is called as a positive sense. We'll take it as a positive sense. If it is pitched out motion, then we take it as a negative, that is anti negative sense. There is a sign convention that we need to follow. And lift force. Generally, people fail to understand that this concept, that is, if you have a free stream, the lift force is the force that is acting normal to the free stream, but not normal to the chord. That is what you call lift force. And the same way, this is your chord line. And the same way, the drag force is the force that is acting parallel to your free stream. This is your U infinity. So these forces we always need to resolve from the normal forces and axial forces. It is a kind of transformation from axial to, like, from one coordinate system to the another coordinate system. So these vectors we need to resolve. So how you can resolve from normal forces and axial forces to lift and drag is lift is equals to n cos alpha minus a sin alpha, and drag is equals to n sin alpha plus a cos alpha, right? So this is coordinate transformation. If you are able to recall that how to transform the coordinates from one particular, or it's a kind of rotation. Instead, I can say simple rotation kind of matrix, that if you want to rotate from one axis to another axis, that you can use it. And center of pressure, you need to understand the definition of center of pressure. Center of pressure is some point on the chord line. Suppose if it is, this is my center of pressure, I denote it as xcp, some dimensional format I'm trying to tell now. If this is I'm calling a center of pressure, then what characteristic it should have? It means the resultant force, whatever the resultant force due to the pressure distribution, like I can get pressure distribution at every point, and if I multiply with a small elemental area, then I will get the elemental lift force or elemental drag force at that point. So if you integrate all these lift and drag forces at every point, you will get one resultant vector. That is, we generally say that is a resultant vector. We always need to recall that what is our resultant vector also. If you can recall that resultant vector is a vector that by integrating all the forces on top and bottom surface of the airfoil, and then if you take a summation of it, you can find the resultant vector and its position. Once you get the resultant vector, from there you can resolve lift and drag forces. Okay, if the resultant vector, the position at which this resultant vector is acting, suppose this is how my resultant force is acting, that location is called center of pressure. If the resultant force is acting here means the moments at this point are zero. You must keep in mind these things for your entire course, later on also for your better visualization of what happening in this aerodynamics. Moments at CP are equals to zero, and the resultant force acts here. Okay, and then we have aerodynamic center. Aerodynamic center this is also some point on the chord line at which your change in moments, that is dm aerodynamic center, we represent with the suffix ac, sorry, subscript ac with angle of attack. If you are changing your angle of attack, the moments about that point should not vary. This one we call as aerodynamic center. Some point we can find that, and center of pressure, aerodynamic center. Okay, you should note that you should get a question whether center of pressure is fixed if you change the angle of attack. No, center of pressure also varies, but it's not significantly varies if you change the angle of attack. After certain angle of attack, it varies very significantly. In the same way, the aerodynamic center also not significantly vary for a small angle of attacks. And if you want to calculate the moment about leading edge, we use the formulation like this: moment about leading edge equals to movement about the quarter chord point. It is a common idea to calculate to take the results, resultant forces or resultant, mm, like every time in the experimentalist, they used to take the data at the quarter chord point. By the time you now realized why we are using the quarter chord point with the derivations of, uh, if you've gone through the derivations in the class, there we see at some point if we do a by do a naught, it's not do a naught, like if you are trying to solve for some point where the movements are going to be zero, like you should start with this idea: do MAC, that is moments about aerodynamic center, or some point on the chord location, that is x. See some point on the chord location where that movements are going to be zero, then you can understand that the resultant location is the quarter chord point. It yields the quarter chord point from our theoretical analysis. So that's why we always see the quarter. We always take the forces and measurements as a standard as quarter chord point, and that is fixed. Not against a fixed. It's a convention that people are using for any kind of aerofoil, so whether cambered or symmetric. So if your quarter chord point has no movements, then like movements of quarter chord point and aerodynamic center, sometimes you will get same, that there is no presence of movements or uh, XAC or MXCP. These three things will combine for certain cases in a symmetric aerofoil. These three are equal. That means, though definitionally these three are different, that quarter chord point, aerodynamic center, and center of pressure, definition wise, those three are different. The three will merge for low angle of attack and for symmetric aerofoil and some conditions, these three are same. That is again the quarter chord point, that is MC by 4. This is already defined, but these two locations are not defined. But for low angle of attacks, I'm mentioning that these all three are same. If you are trying for high angle of attack, these things vary. So MC by 4 is a quarter chord point, that is fixed. Okay. And then we should also understand the characteristics of any curve, any lift curve of an airfoil, that is with respect to alpha and angle of attack CL. It is going from the origin, then we say it is, we can easily say it is a symmetric aerofoil. If it is not going from the origin and going from somewhere with respect to by crossing this x-axis or something, then we can say it is a cambered aerofoil. This lift, the lift present at zero angle of attack, is also important to designate that zero lift. We can say it as a zero lift. Sorry, alpha at zero lift. This is CL, not we say. At zero angle of attack, we are having some amount of lift. That lift is zero lift, we call, and that value is positive or negative, depends on the camber, whether it is a positive camber or negative camber of the airfoil. So it will helps to indicate or designate what kind of aerofoil that you are using. It's very important. And then you need to understand the pressure distribution on the aerofoil. We already discussed this. Why it is important to understand the pressure distribution. This will give you the correct idea of how much of pressure gradient is happening. This pressure gradient will give you the understanding on the presence of adverse pressure gradient. If it is this gradient, you see there is a sudden drop of pressure in the small narrow region. Like if you change from very small region, there is a very sudden drop of pressure. This is what we call the pressure gradient, high pressure gradient regions. If there is a presence of high pressure gradient regions, you can see the presence of, there are more chances of seeing the flow separation. This is the negative value and this is the positive value. This is the pressure coefficient, we say. Okay. And the pressure coefficient can be linked from our previous understanding with respect to Bernoulli. We derived that pressure coefficient is U by U infinity square. Okay. And now let's go to different kind of series in the airfoils. That is NACA 4 series, NACA 5 series, NACA 6 series we also have, but I will discuss 4 and 5. Okay, 4 series we have 4 digits. This, you know, this last 2 digits is always significant that we see. It is indicates a percentage of thickness. If these 2 digits are 0, that means it is indicating that the airfoils are symmetric. If these first 2 digits are not 0, or if it is the presence of some values, then it is a cambered airfoil of the 4-digit series. Then what is that camber? It is a maximum camber in hundreds of chord. And this is the maximum camber location in tens of chord. So your chord is the key parameter that you are defining all other parameters in terms of the chord only. So if you want certain chord length, then all your remaining parameters are also decided. Okay. Then how you are generating this aerofoil is also key interesting concept. Like with these 4 digits, you are able to generate all the coordinates of x and y. Is it possible? How they are generating this all the coordinates? Suppose if you are considering this is your x and y plane, and these are all your coordinates starting. Suppose this is your coordinates point p1, this is your point p2, point p3. In the x and y plane, to generate this aerofoil, you need all these coordinates. How these all coordinates? Suppose if I want 100 coordinates, I can point 100, I can mark 100 points on the aerofoil. But how all these points are generating? By just using 4 digits or 5 digits in the 5 series, or 6 digits in the 6 series. This is also an interesting concept you can learn on by your own. For this, you can refer airfoiltools.com. It is very interesting concept to learn how small number of digits are deciding the these many points, and how we are fitting these curves with the small number of configurations. Configuration means the 4 digits or 5 digits. That's what we call as a configuration. And for the 5 digits, if you go for 5-digit aerofoil, the first one is, let me say, A, B, C, D, E. The first one designates, if you multiply it by 3 by 2, the first letter, whatever the first letter value, if you multiply it by 3 by 2, you will get the design lift coefficient. Design lift coefficient. By this time, you should understand why this design lift coefficient came into the existence of the 5-digit aerofoil, which is not present in the NACA 4 series. This can give you a sample or a rough idea of the amount of lift or amount of lift coefficient that can generate by the aerofoil based upon a crucial definition is there for how you are stating that design lift coefficient for an aerofoil. So I suggest you to go through this definition in the lectures. It's very interesting how one aerofoil, any aerofoil can be uh, identified, like how much of design lift coefficient it has. You can go through the definition, and the remaining 4 digits are okay. Seems I did not write the remaining 4 digits. Okay. Anyway, I will re-verify these 4 digits, and I will let you know this what are the 4 digits are indicating. I cannot recall it now, but two things are uh, D and E. Again, mostly common things is the last 2 digits are indicating your thickness of aerofoil in percentage of the core. This is common that you can easily figure out what is the first last 2 digits parameter is always thickness of your the aerofoil. Okay. And then we have the characteristics of aerofoil for an infinite wing without ends. That is what we call as airfoil. And the inviscid theory predicts, can predict. We already, maybe if you gone through the complete derivations of how the inviscid theory worked out for a finite aerofoil and how it was modeled, you can see that dCl by d alpha equals to 2 times a, that is also is a 2 pi. It is called also called as a naught dCl by d alpha, that we can model how we came to this conclusion that dCl by d alpha equals to 2 pi. What is this dCl by d alpha? We are writing, or we are plotting this alpha versus lift curve for many aerofoils like this. So what is deciding this slope of this linear region? Anyway, this is a stall region. This stall region cannot be predicted by the theories that so far developed in the class, but the slope and the lift coefficient theoretically predicted as dCl by d alpha equals to 2 pi. So it is one of the important criteria that gives at least a overall a simple our idea of the lift coefficient that can generate by the wing or an airfoil at that angle of attack. And we have aerodynamic efficiency. Aerodynamic efficiency is nothing but the ratio of lift to drag, which also varies with the angle of attack. And then moment about the aerodynamics center. If you want to calculate the moment about the aerodynamic center, is equals to, from the experiments we can get moment about the quarter chord position, and we also can get the lift, and that is CXAC, that is the aerodynamic center that we say, and C by 4. How we can calculate that? We are having a XAC, that is aerodynamic center, and we have MAC. Both are two are unknowns here. How we can calculate both unknowns? We can use additional equation. There are two unknowns, and we also have additional equation is equals to 0. So using these two equations, if you take one more reading with a different angle of attack, and this is suppose MAC1 and MAC2, and try to take the reading at one more angle of attack, and if you see that MAC1 equals to MAC2 and equate those two equations, then you will get the location of aerodynamic center on the aerofoil. This is what experimentalist, if they wants to design any aerofoil and they wants to find out its characteristics, that's how they do calculate this aerodynamic center. And in the non-dimensional sense of the same thing, coefficient of moment about aerodynamic center, if I write just in the non-dimensional way, this is CL times XAC minus 0.25. This XAC, you remember that I multiplied here with a chord. That means it is a non-dimensional one. So here CL is not present. That means it's a non-dimensional alone. It's not a dimensional parameter. And for further analysis, like the same thing that I wrote here, dou MEAC, that is moment about aerodynamic center. If you partial differentiate the moment about aerodynamic center, then you will get the definition itself is it should be 0. That I want to apply the same for this non-dimensional way of moment about aerodynamic center. If I apply that, what I will get Cm at c by 4. Cm comma c by 4 means that is coefficient of moment at quarter chord point. Okay, so once we substitute the dCm by dAc equals to 0 and the dCm by d alpha, this is m naught, and dCl by d alpha, it is a naught. We already described here that is dCl by d alpha equals to a naught, this one. And so in the same way, moment about the quarter chord point can be stated as dCm by c by 4 by d alpha is m naught. Then you can find a position of aerodynamic center with this simple equation. Why we need the aerodynamic center? Because it gives a point where your movements are not changing. So it will help you for designing of an aircraft or for a stability purpose. It is very required because forces can be vary, but movement should not vary. Flight stability kind of purpose or any aircraft kind of stability purposes, these parameters are so useful that you can go through the next stability kind of courses you take. You can understand how this aerodynamic center of pressures are very important for designing the aircraft. So this is up to the concepts that we covered for the baseline aerofoil. Or it's not a baseline aerofoil; it's a aerofoil with a like infinite wing aerofoil or an infinite wing. Then we have the primary flows. Very briefly covered. Now, the primary flows are what we are having are uniform flow. We are having a uniform flow, and I'm not going to the details of derivation. Uniform flow, this is what it means. It should be oriented in any particular direction, either it can be X or Y in any direction, but it should not vary with respect to your space. And it should be a steady flow. It no need to be aligned along your X direction. It can be aligned your Y direction. It can be aligned your any kind of XY radial direction, but its velocity vector should not change at any point with respect to time also. That is why that is what we call as uniform flow. And if you try to identify its stream function, the stream function, if you draw in this uniform flow, you can see that at every stream function there is a specific value constant, and there's the importance of it. Like you can identify the mass flow rate based upon this stream functions, and the potential function phi is given as phi equals to u infinity into x, and see that potential function is perpendicular to your stream function, and it crosses where those intersect. At these points, at these intersection points, the potential lines, potential function lines, or the stream function lines are perpendicular to each other and they intersect here. And then one more interesting definition is, if you see del phi, that is C2 minus C1, will give you mass flow rate between those two streamlines. Per unit depth to the page. Not only for the uniform flow, for any kind of flow, if you know the stream function, you can relate that with the mass flow rate at that point. Okay. And one more thing that you need to understand, there are two things. That is, for an incompressible flow, if you are using an incompressible flow, then stream function psi equals to psi bar by rho. That means the psi bar is just you're multiplying with your density. Okay, right. And then you have source and sink flow. Source and sink flow conceptually they look same. The only difference is if the fluid is emerging from a single point radially in all directions with equal volumetric flow rate. How we are mathematically quantifying it? If you draw any line or any circle like this, the amount of fluid that is crossing at any point or the volumetric flow rate at any point or through this circle 1 or circle 2 should be same. That we designate as sorry that we designated as capital gamma. This we call capital lambda volumetric flow rate per unit length. Okay, so with this, if you want to identify what is the radial velocity at any point, that is given by Vr equals to plus or minus capital lambda by 2 pi r. So why this plus or minus? What is it indicating? Is plus indicates the volume flow rate, that is for the source. That means plus indicates for the source, that is volume is flow rate is towards the radial direction, the positive r direction. And if it is negative means that is sink. Fluid should sink radially, should come inside and disappear at this point, and the same conceptual again works. The volumetric flow rate should be same if you draw any circle around this sink. Okay, this is what the idea. So we are this for the sink. Sink is for indicates a negative. And since it is in polar coordinates, it is very convenient to write the potential function or the stream function in polar coordinates. That is dou pi over dou r equals to Vr. And so you can get pi equals to capital gamma pi ln of r. This r is your location. Sorry, capital lambda by 2 pi ln of r. R is your radial location at any point. If you see, take a radial location here, and this is your axis, and this is your theta. This is your theta, and this is r. That is corresponding to. We will give you the pi value at that point. The streamlines. How you can identify the streamlines? Streamlines are in the radial direction because streamlines are all parallel to your velocity vector. So your streamlines are all in the radial direction like this for the both source and the sink flow. So potential lines are in perpendicular to this radial lines. That means the circles. These are all potential lines, pi 1, pi 2. The same way for the sink also. Streamlines are the radial lines and the potential lines are the circles. And the third one is a doublet. A doublet flow. Before going to the doublet flow, you also need to see what is a Rankine oval? Suppose if you are placing fluid uniform flow with U infinity over the source, suppose this is your source flow and your fluid is emerging like this, you're allowing the free stream on top of it, that you will see a Rankine, semi-Rankine oval. This is your free stream flow. So all the streamlines emerge like this, and this we called as one particular line, the streamline that has a zero stream function. This has a stream function of zero. That particular line we call as a semi-Rankine oval. In the same way, if you have a sink here that has fluid coming radially towards inside, then whatever the semi-Rankine oval will converge at this point like this. Sorry for the drawing. This semi-Rankine oval. Sorry, this is the complete Rankine oval. If your length between this sink and source is L. If you combine or if you move this source and sink to the infinitesimally very small distance such that the strength is, it is like you are making your distance is very small and the strength of the, that is the volumetric flow rate of the source and sink are very high. This is you are decreasing and you are increasing, and both combination should give some constant value that will give you the strength of doublet. How doublet looks like? It looks like this. The vector will point out in this direction. So all these circles will merge at this point. This is how your doublet looks like. Okay. So the doublet phi function, that is stream function, is given by minus k by 2 pi sine theta over r. If you want to clean derivation of every stream function or potential function, I suggest you to go through the lectures, or you can go through this book, Fundamentals of Aerodynamics. You can refer these books and you can practice the derivations on your own if you are interested, or mathematically. These are the conceptual. This course will give you the some mathematical concepts of every aerodynamic parameters and a physical overview of the things what going in the flow over and bluff bodies, or flow inside or internal streamline bodies, everything. Physical overview and mathematical concepts, if you can relate in a proper way, you can achieve the objectives of this course. Okay. So this is the potential function and this is your stream function for this doublet. Then we come to a vertex flow. Before going to the vertex flow, I just want to show you that cylinder, like how flow over cylinder can be generated. Flow over cylinder is a combination of uniform flow and doublet flow. Okay, so if you are generating flow over a cylinder, that means it's a combination of uniform and doublet flow. Suppose your doublet has a vector here and it is, sorry, this is like this. Okay, and you are impinging or you're allowing a uniform flow through this. That will create, those streamlines will create a zero streamline function or zero streamline. That is the stream function of this line, the streamline is zero. That acts as a boundary, or it looks a cylinder, circular cylinder. And this flow over a circular cylinder we achieved by combination of uniform flow and doublet flow, and the corresponding uh, things are like this. If you want to quantify what is the radius of the circular cylinder, that radius is given by root of k by 2 pi u infinity. What is your k? Your k is, again, you should refer this one, the strength of the doublet. And u infinity is your free stream velocity. That will give you a the flow over a circular cylinder kind of phenomenon. And you will see two stagnation points, one at here and another one is here. And you should note that Vr equals to 0 on this entire circular cylinder. That is, radial velocity is 0, and V theta is equal to, that is, velocity on the circular cylinder in the tangential direction. V theta equals to minus 2V infinity sine theta. At the same time, using this V theta and Vr, if you want to find out the pressure distribution, we can use, okay, so we can use Cp equals to 1 minus V by V infinity square, where V infinity is your free stream velocity, and V you can find out by taking the magnitude from the Vr and V naught, V theta. If you do that, you will get Cp is equals to 1 minus 4 sine square theta. This is very important pressure coefficient distribution on the entire aerofoil, entire cylinder theoretically. You can try to match with the experimental data also. This matches very beautifully for upper surface, like up this surface, this upstream surface. For the downstream, because in practical sense, you will see the wake because of the viscous effects and the pressure gradient. You will see in the wake in the downstream, so you're not able to see the pressure coefficient matching with the theoretical result. But like, for the upstream side of your cylinder, this side, it matches beautifully if you do any experiments, if you try to conduct experiments on the flow over a cylinder, any solid cylinder. That's how theory helps us to understand previously before conducting some experiments or validating our mathematical models. Okay. Next, we have vertex flow. That is the fourth one. Vertex flow is in contrast to your source flow and sink flow. If you have a point vertex here, it has only Vr and V theta. Vr equals to 0. You should note that because we are dealing in the circular or polar coordinate system, because the flow field is looking uh, easier to deal in the polar coordinate system. So we are writing Vr and V theta. Until now, we wrote Vx or U and V components, but you should able to change from the Cartesian coordinates to polar coordinates in this. Sometimes spherical coordinates also required in this aerodynamics. So you must be able to switch from one to one in a convenient way, or you need to understand how to transform from polar coordinates to circular coordinates. So V theta equals to, we will say, that is some C by R, where this constant C is the important parameter that defines or that gave us the concept of circulation. How the circulation is defined is integral, line integral d bar dot ds. Since it is your circle, I can write gamma equals to, if I do the line integral about ds, if I take any small elemental ds on the circle, and the v bar is constant, that is v bar equals to v theta. So I will write as v theta, and integral ds means the small element, if you integrate over the entire circle, you will get perimeter of that circle, that is 2 pi r at that point. So that's how this circulation came into the picture for defining the strength of the vertex. So if you define the strength in that way, you can get circular by just replacing this v theta is equals to gamma by 2 pi r. A very important definition for the vertex flow, not only for the vertex, we are going to use in uh, for a baseline, not sorry, for a finite wing kind of conditions where the wing tip vertices you can see. And then yeah, same thing here, strength of a point vertex. Okay, next, the phi function, that is potential function, the potential lines. Now the velocity vectors are like this in this vertex flow. Those are only tangential to your theta direction of the circle. So your streamlines are also pure circles in this vertex flow. Then your potential lines are radial lines, because your radial lines and streamlines are perpendicular to each other. Then the formal equation that came out for this vertex flow is potential function pi equals to minus gamma by 2 pi theta. Okay, and stream function psi equals to gamma by 2 pi ln of r. So until now we see uh, how to calculate the pressure distribution. This is the pressure distribution on the circular cylinder. But what will happen if you merge this vertex flow, that is spin, with a circular cylinder? That means you are creating a spin in the flow field. In the uniform flow field, you are creating the spin by using this uh, vertex. Let me try. Spinning cylinder in uniform flow field. What will create? It will create a net pressure difference, and it will create a lift on the spinning cylinder, and the corresponding flow will looks like this. Your stagnation points, earlier the stagnation points are on the diameter axis, but now it came to these two positions. And if you draw the remaining streamlines, they looks like this. You see the turning of the streamlines. If the streamline is turning with a high radius or high radius of curvature, and if it is a fast turning, then you can, it's a kind of rule that velocity is so high at that point. Based upon the curvature of the streamline, you can decide that the velocity is very high at that particular point, and it's in the direction of the tangential to the streamline. So this is how your flow field looks like if you impose this vertex in the flow over a cylinder kind of situation that we seen before. And then you will get the pressure distribution Cp equals to 1 minus, earlier we seen up to here, that is 1 minus 4 sine square theta, that is the pressure distribution for non-lifting flow over the cylinder. If you are doing for the lifting flow of cylinder, this becomes lengthier like this. Okay, this is the lifting flow over cylinder pressure distribution. This is a part of pressure distribution for a non-lifting flow over a cylinder. If you integrate for a drag, you will get drag CD equals to 0. But when from this theory, we also mostly heard about that D'Alembert's paradox, where from the experimental results of flow over a cylinder or flow over a spinning cylinder, like spinning cylinder or a static cylinder, that we see a significant amount of drag. That is, drag is equals to finite from the experimental result, where we can have the viscous effects and other effect pressure drags also. There, your drag is a finite, but theoretically it shows the drag is zero because we did not consider any viscous effects while deriving this uh, forces on or the pressure distribution on the spinning cylinder. So that this kind of is mostly famous in aerodynamics, like the D'Alembert's paradox about this finite drag or the zero drag that we call as the D'Alembert's paradox. And then we have CL equals to, from this is we called as Kutta-Joukowski theorem, that which in the first time that we got a relation of CL based upon that relates the circulation and some characteristic length r and the free stream velocity. What is the non-dimensional lift coefficient that you will get if you have some circulation on your body or a circulation in the flow field and some characteristic length of the body and the free stream velocity, that is relating beautifully with all the simple parameters that present in the flow field. If you write in a dimensional way, lift per unit span equals to gamma rho infinity u infinity, the lift over on the cylinder, that we say as Kutta-Joukowski theorem. Fine. So note that this is lift per unit span. This is not a lift entirely. This is only the lift per unit span, and that is up to the modeling of Kutta-Joukowski theorem. We will see today one more Kelvin circulation theorem, and then we can go for the doubt clearing sessions. Any doubts? Like now, Kutta-Joukowski theorem we just seen. So the idea is still not clear how to implement on aerofoil of the same thing that we seen for the flow over a cylinder. So to model an aerofoil, we can use many primary flows. Like if this is your aerofoil, the condition is the flow should not penetrate through this aerofoil. So it is modeled by point vertices on the entire flow field. To satisfy these conditions, all the points on the aerofoil are having a point vertices, and it is still difficult to manage, like for entire aerofoil we don't know the curvature defined properly because it is an arbitrary curvature. So it gives a complex geometry of how to handle these points vertex on the complex, I mean this kind of complex surface. So to simplify it further, it shifted to camber line. If there is a camber line, we shifted to the camber line. For further simplification, it is shifted to the chord line. Basically, if you say this is more suitable for the symmetric aerofoil, if you try to model this. Now, the condition that we applied is the fluid element should not pass, or any flow vector should not pass through this camber line or the chord line. So, if I am allowing some fluid velocity, mathematically I'm allowing some fluid velocity u infinity, this u infinity is having a tendency to go up because I'm inducing with some angle alpha. So u infinity sine alpha has a tendency to move through this chord line. But according to our mathematical model, how we should define this, the flow induced by all these vertices at this point should, if you do the combination of it, that is u infinity sine alpha plus w of y, that is w of y is induced velocity because of this point vertices in the downward direction. Combination of both should give 0. This is our basic step to proceed further of modeling the flow over. You can model the flow over airfoil, or you can also calculate the lift coefficient on the aerofoil. From this understanding, we also got an ambiguity of how to deal with the trailing edge. It is now clear to model how to flow, modeling the lift coefficient of the entire airfoil, but how to handle this trailing edges. There are two concepts we already discussed very long back: how to handle the sharp trailing edge or the cusp trailing edge. For a cusp trailing edge, we know that from the Kutta condition, uh, the flow should leave the trailing edge smoothly, and the circulation at the trailing edge should be 0. Circulation is also identified or defined as a jump in the velocity and the up and the down slips. So the velocity at this point, V1 and V2 from the upstream and downstream, V1 should be V2 equals to 0. In the same way, to make the circulation at this point as 0, which are not going to merge together because of this cusp trailing edge, and we should make the trailing velocity, so circulation at this point is 0. We should have V1 equals to V2 equals to 0, because we know that circulation per unit length, this is a small circulation per, sorry, this is a circulation per unit length, that is gamma is equals to slip in velocity, that is V2, sorry, U2 minus U1. To make this gamma at the trailing edge 0, you should have the same velocity on the top and bottom surface, or either V1 and V2 equals to 0 for the sharp trailing edge. This is a Kutta condition that we see. And also from the Kelvin circulation theorem, we've seen this bound vertex concept that we have been discussing, and then the starting vertex. This is the starting vertex. If you, from the Kelvin circulation theorem, if you trace the particles from the initial time, the substantial derivative, like if you need to calculate the circulation, if at time t1 there is no starting vertex, and you have a particles that you trace like this, whatever the dotted lines here, and at time t2 also you trace the same particles and you calculated the circulation within the same particle, then according to the Kelvin circulation theorem, d gamma by dt should be equals to 0. That is, gamma at time t1 should be equals to gamma at time t2. There should not be any change. But if you see the individual airfoil alone, there is some presence of lift because of the free stream, that is u infinity. This free stream creates a bound vertex or a presence of lift on the aerofoil. This we call as a bound vertex. With this bound vertex, you are getting a lift by using the Kutta-Joukowski theorem, that is lift is equals to uh, sorry rho infinity u infinity gamma. As you have gamma is coming from the bound vertex, that you are getting the lift on the aerofoil. But according to the Kelvin circulation theorem, this is Kelvin circulation theorem, your circulation should not vary. This should be compensated by some other vertex in the flow field. That is what we call as starting vertex in the flow field. You can see this experimentally also by any YouTube videos. I will show this starting vertex and bound vertex, or stopping vertex also in upcoming lectures. And this Kelvin circulation theorem is very useful in not only for modeling this finite aerofoil, I mean, infinite aerofoil. For finite wing also, we are using this Kelvin circulation theorem as a base to construct its modeling. So now I'm going to stop here. We still have so much to discuss, but in the next lecture we will see some problems on this. After covering one more simple airfoil theory and discussing about cambered airfoil and pitching movement, and then we will see some problem sessions on this. We will continue to see the problem sessions more for your better understanding in solving the assignments and the questions in uh, these thermodynamics, like where you started from. That's week 7 lectures, I guess. So from there, we will see all the discussions earlier by skipping some content of on this baseline aerofoil. Okay, as we are lagging. So we will see the mostly problems from the next session. So I will now stop here, and we will take any questions uh, from you all. Arshit, are you there?
Yes, sir. Yes, sir.
Okay. So as I promised you, I would like to discuss. Like, can you repeat your question once again? I need to discuss. Uh,
Yeah.
uh,
That quasi one-dimensional flow through a convergent divergent nozzle.
okay. For that, I need something like area Mach number relation. Do you know the area Mach number relation? You heard about that area Mach number relation?
Yes, sir. I heard, but I can't recall right now. I heard
Can
about
you at
it. I
least
have
tell me
seen the
the
lectures.
derivation? Okay. Can you at least tell me the derivation of, not derivation, final formulation of it? Is it possible? If not, I will just search for it, because it's not that
No,
you need to remember all the equations. It's up to you, the practice,
no, sir.
and how much efforts you put on this. I just want,
No, sir.
okay, I will do. Number, Mach number and area relationship, if you see, let me get the equation for it. You can see. There is a differential format of equation.
Sir, you are asking for that A star by A means equal
No,
to
no,
M
no,
by
no.
M star, I think.
Yes, that is also one relation that we derived from the basic governing equation I'm looking for. Differential format is there. You can find it in Anderson book, but I will just show you the equation. That is actually given A star by E. This is also a relation, primary relation, but we need here some differential format to understand your question. A by A, it's more or less looks like this. dA by A equals to 1 minus from where they substituted it. Just give me a minute. I'm finding the correct equation. So by looking at that equation itself, you can clarify your doubts. That much things, that those are the details included in. I'm still in class.
Sir, I got that
Yes,
equation. I think.
yes, this is, you got
A
it.
A by A star square equal to 1 by M square plus 2 by gamma plus 1 into
No,
1
no, no.
plus gamma minus 1.
That is
No,
used. That is used.
it is
I'm looking.
written that actually area
Okay.
mark number relation. It is written.
Area Mach number relation, but this is
Yes,
also
sir.
the area velocity relation that governs by. I mean, this differential equation. Are you seeing my screen?
Okay. Yes, sir. Yes.
Yeah, this relation. This is a area velocity relation where Mach number is playing a key role. For this, I'm looking for. So you see this equation. Um, I will just write it here. This equation is saying dA by A equals to m square minus 1 du by u, right? This is the governing
Yes, sir.
equation between velocity and area. From your continuity, what you are saying, you cannot apply that rho 1, A1, U1. That also you can apply. But before that, what is governing is rho 1, A1, U1 equals to rho 2, A2, U2. You want to apply this one, right?
Yes,
You
sir.
are telling.
Actually, I'm seeing the continuity equation is not applicable in this case. I think so.
Not applicable when you are using the compressible flow because you need to consider that density also. It
Yes,
is
sir.
applicable
For
only when you need to.
compressible flow, uh, yes, sir. In viscid
Yes,
incompressible flow, I think it is compressible. It means it can be used.
yes. So density now is a parameter. This can be used for the compressible, incompressible anywhere. This is a mass continuity only for one dimension because you are using the density also here. So rho 1 A1 U1 equals to rho 2 A2 U2. Okay.
Okay, sir.
Okay. Now you see this equation dA by A m square minus 1 du by u. How it is handling? Suppose your Mach number is less than 1. What it mean?
Sir, it will form a negative on the right hand side. Negative minus du by u, something like that.
Okay. If your Mach number is less than 1, it will form
A
dA
negative.
by A equals to minus du by u. Right?
Yes, sir.
Okay. So now your area relation and velocity relation is like this. And if it is Mach number is greater than 1, it will give
Then it will be
some,
positive term.
I will say some
Positive u.
constant K1 and it is some constant K2 du by u. Okay. You see the convergent divergent section. You see here from the continuity, you have another dependent parameter that is density. So you cannot comment completely whether area is varying your velocity directly or indirectly, right? You are in the convergent divergent section, your area is predefined, but you cannot comment directly because density is also playing a key role.
Yes, sir.
Okay, this is not du. This is u. So I will write the first equation, and this is the second equation. The first equation is I will write du equals to dA by A 1 by K times u. This is for Mach number less than 1. Suppose if you have a dA by A, that is a small area is decreasing. You see this one. Decreasing means dA is negative, dA by A is negative. If your A2 minus A1, always follow the convention. If A2 is less than A1, that is A final minus A initial. If A final is less than A1, that means suppose this is my A final and this is my A initial. AF minus AI. This is my sign convention. AF minus AI means I will get minus DA, right? If you
Yes,
are
sir.
getting a if you are getting a minus DA by using in the convergence section, substitute the same. So as your area is decreasing, this will give you a minus of minus DA by A. This is all constant. I'm not going to change it. So your velocity is now becomes positive. That is du is positive. What it means, du is positive means your change in velocity is increasing. That means whatever the velocity at initial should increase between from this to this. You got
Yes,
it?
sir.
If you
Yes,
apply
sir.
the reverse, same thing in equation 2, what will happen? Just
If,
apply the same according to the equation 2.
yes, sir.
Velocity
Okay,
will
sir.
increase or
For
decrease.
velocity will means for equation two.
if you use
If
now, I use the equation 1, that
velocity will
will
decrease, I think, sir. Velocity will
velocity
decrease
will
in that
decrease.
case.
Follow the sign convention as it is. Don't
Yes, sir.
get confused. My initial area is this one, AI. I'm taking two areas, and final area is this one, AF. AF minus AI. If my final area is less than initial area, what I will get? Negative value or positive value?
If final area is greater than initial
Less,
area, then
less than. My final area is less. It is smaller. What is the
okay.
cross-sectional area of this?
Yes, sir. We'll get negative area value means minus
We'll get
dA.
the negative area, minus dA. That's what the
Yes,
same
sir.
I'm substituting in the equation 1. Equation 1
Okay.
I rewritten as du equals to, that is change in velocity equals to minus of dA by A 1 by k times u. I'm just substituting my dA is now negative dA because my final area is less than initial area. So I'm subtracting smaller one from larger one. So I'm getting a negative dA. I'm just substituting the same negative dA instead of dA. So I will get this term. What will get? You will get this term as a positive. That means your dA is positive if you take the equation 1. What is equation 1 corresponding to?
Equation one, sir.
I think you are not clear.
Yes,
Okay,
sir.
okay. You are
Sir,
not clear, I think.
equation no, sir. Equation for equation one, you have taken that subsonic flow,
Subsonic
and
flow, Mach
equation
number less than 1.
yes,
Yes,
yes, sir. And for equation two, it is a supersonic flow.
the supersonic flow. So if I am taking the subsonic flow, how it is behaving? By decreasing area, subsonic flow, it is increasing its velocity, right?
Yes, sir. Yes, sir.
And the same for supersonic flow, it is all acting reverse. If I'm decreasing my area, it is decreasing its velocity also.
Yes, sir.
Just try to play with this equation. You will understand it clearly. This is the key
Yes,
governing
sir.
equation.
Got
Okay,
it, sir.
got it?
But sir, what in case? But in case of the throat area, in case of
Okay,
throat area, the if the Mach number becomes one, it
okay.
is sonic. Then
It
dA
is
by
sonic.
A equal to zero.
There you cannot apply this. At the throat, it is a
Okay.
transonic region. You
Okay.
need to handle the things very carefully. Whenever in the mathematics, if something is going to be zero in the denominator or the numerator, you should handle the mathematics very carefully.
Okay,
For the
sir.
transonic region, we cannot apply this directly. It is going to be yield zero and dA. That does not exist. The equation becomes indeterminate. There will
Yes,
be
sir.
no solution will exist. You cannot say this is happening. So you should not apply for this transonic region. Transonic region has different relations. Okay. So for the
Got it, sir.
supersonic and subsonic, you can handle this. Fine.
Okay, sir.
Okay. If
Sir,
any queries, yes.
sir, yes, sir. Another thing, sir,
Yeah.
in that video lecture, I saw that in case whenever there is the velocity is passing through the throat at
Okay.
sonic velocity, the mass flow rate becomes constant and it becomes a choked condition.
Yes.
That that I couldn't understand means the concept.
Choke condition is like it's if I say simple terms like can you eat more than that you can feed into your throat?
No, sir.
That is the same thing happening. Just for your understanding, the same thing happening in the
Okay,
kind of if you are
got it, sir.
having yeah, it depends on the fluid. Though you are decreasing your pressure, I'm decreasing my pressure pre-exit and P naught. I'm decreasing my exit pressure or increasing my pressure at the inlet. How much you increase based upon the characteristic of the gas after reaching certain mass flow rate m naught. There is a derivation for this also. You can refer to it. Some maximum mass flow rate m naught. It cannot reach. It cannot take much more than that because it's the area constraint or the gas constraint. Everything depends. But velocity may increase. At the same time, density and velocity, those parameters differs. But this maximum mass flow rate will choke here. That condition we say called as choke condition. Okay.
Yes, sir. Yes, sir. At sonic regime for in that
Sonic
case.
regime. Yes. Okay. If any further queries, please post in the uh, Google Docs or Google Forms. I will
Okay, sir.
solve this in the next lectures. Okay. Thank you, Rohit.
Okay, sir.
Thank you, everyone, for
Thank you,
joining the
sir.
session.
Thank
Okay.
you, sir.
Thank you.